Hello, this is Majid Ashale, and I will be covering question 10 from the chapter 22 of Gauss's law and electric flux. So, this question right here is talking about a graph that shows the electric field strength as a function of distance from the center for a pair of concentric uniformly charged spheres. And is asking which of the following situations could the graph plausibly represent? There may be more than one correct choice. So we have to analyze this situation. So it's showing electric field strength as a function of distance from the center of a pair of concentric uniformly charged spheres. So we have to create an image. So we have the center of the sphere, which is right here. And then you have two uniform spheres, two pairs of uniform charged spheres, one on the inner and one on the outer. And in this sphere, we have a conducting sphere that's positively charged, which is the inside. And then on the outside, we have an uncharged conducting sphere, which is this one. This would be this would be uncharged, and this would be positively charged. So now we're being asked, which of the following situations could the graph possibly represent? So over here, we see that in the first graph, which is right here, the first graph right here, we see that its amplitude is more than the second graph. So we say graph 1, and then this is the second graph right here, graph 2. We see that the amplitude is more than the amplitude of the second graph. And when the amplitude of the first graph is more than the amplitude of the second graph, it shows that the outer sphere does not have a positive charge. And over here, you can see that the outer sphere, which is here, it doesn't have a positive charge. It doesn't have any charge. Therefore, it is uncharged. But the first graph has a higher amplitude, which means that the inner sphere is positively charged. And it's also the center. So for here, we can say that a positively charged conducting sphere within an uncharged conductivity sphere. So a positively charged conducting sphere, which is this one, and then an uncharged conducting sphere, which is this. So here, this would be an option. This would be one of the options. And another scenario that we can have for this is that we can have a positively charged non-conducting thin wall sphere inside of another positively charged non-conducting thin wall sphere, which would be this option. And these are the two following situations that could be represented by the graphs possibly. And then we'll move on to question 20, which talks about two extremely large non-conducting horizontal sheets, each carry uniform charge density on the surfaces facing each other. The upper sheet carries +5 positive charge, which is nanocoulombs per meter squared, and the electric field midway between the sheet is 4.25 times 10 to the 5 newtons per coulomb, pointing downward, and asks what is the surface charge density on the lowest sheet. And we're giving the epsilon value, which is 8.85 times 10 to the negative 12, or we can say 9.0 times 10 to the negative 12. Since we're looking for the surface charge density of one sheet, and we're giving the charge density of the upper sheet, we use the equation E sub t equals E of 1 plus E of 2, which is also synonymous to sigma over 2 times epsilon plus sigma negative over 2 times epsilon sub 0. And then we move on. This equation can then be written as sigma negative equals 2 times epsilon 0 sub 0 multiplied by E sub t minus positive sigma. Oh, minus. This is a minus positive sigma. And then when we substitute in the values, we get sigma, not a 6, negative equals 2 times the value of epsilon, 8.85, times 10 to the negative 12, put a 12 there, multiplied by the electric field midway between the upper and lower sheets, which is 4.25 times 10 to the negative 5 power minus the charge of the upper shield, the upper sheet, which gives 5 times 10 to the negative 6. Since it's micro, it's 1/millionth times coulombs per meter squared. And then as the calculation is done, we get sigma, that is 6 sigma negative equals 2.52 microcoulombs per meter squared, which can also be written as sigma equals negative 2.52 microcoulombs per meter squared. And there you have it. This is the surface charge density on the lower sheet. So we have negative 2.52. And there we go. There you have it. Hope you enjoy.